Hello everyone. Today I'm going to try and share with you what I learned uh, for the rough Bergomi equation. The goal is to bridge the gap between the empirical volatility skew that we observe in the market and the rigorous math of the rough fractional stochastic volatility. So hopefully by the end of this presentation, you'll understand the exact mechanism of this formula. So let's start with the fundamental flow of the traditional stochastic volatility models, such as the Heston or the Standard Bergomi models. If you look at this graph, traditional models produce an at-the-money volatility skew that flattens out and becomes bounded as the time to expiry approaches zero. However, the empirical S&P 500 data tells us a different story. The reality is this one here. The short-term at-the-money skew exhibit a steep power law blow-up. So the market demands a skew that behaves proportionally to RH minus 1/2, which classical continuous diffusion simply cannot generate mathematically. So to solve this, we must shift our paradigm and look at the Hurst exponent, denoted as H, standard Brownian motion, which drives traditional models as a Hurst exponent of exactly 0.5, resulting in a relatively smooth, continuous paths, but market microstructure reveals that variance is actually rough. By shifting H significantly below the 0.5, we transition into a fractional Brownian motion whose paths perfectly mirror the highly jagged anti-persistent microstructure of the actual market volatility. So this table summarizes the core architectural differences. While the standard Bergomi model relies on the exponential kernel, and the standard Brownian motion, the rough Bergomi replaces this with the power law kernel, mathematically written as this, t minus s to the power of alpha. This seemingly small change drops h below 0.5, successfully generating the RH minus 1/2. So the power law blow up at the money skew. However, we pay a heavy price for this realism. We lose the Markov vanity structure. So the rough model has infinite memory, making it computationally demanding. So here is the core engine of the rough Bergomi model, the spot variance equation. To deeply understand this, we will deconstruct it into 4 distinct elements. We think of this as the baseline curve of or the foundation. This part is the amplifier or volume knob. This one is the memory engine, and this one is the martingale anchor or the stabilizer. So let's see each one, starting with the first parameter, which is the baseline curve. So by definition, this is the initial instantaneous forward variance curve observed in the market at time t0. Its role in the machine is to anchor the stochastic process to the observable market reality of the day. So it ensures that the model correctly prices vanilla options at interception. In practice, for numerical stability in simulation and calibration, it is often assumed to be entirely flat, simply a constant. Um, Now we need to look at how the Earth's exponent, so the h, dictates the Volterra kernel through the mathematical link of alpha equals h minus 1 over 2. Because h is strictly between 0 and 0.5, this parameter must be strictly negative. So the domain would be between minus 0.5 and 0. This negative exponent is the defining feature of the model. It forces the Volterra kernel to blow up to infinity as the pastime approaches S. It approaches the current time t. The singularity is the exact math mechanism that creates the jagged non-differentiable paths necessary to generate the steep short term at the money skew. Now, looking at this term here, which is the volatility of the volatility. So its role is to control the magnitude of the stochastic shocks applied to the variance process. As you can see here in the graph, adjusting this parameter acts like a volume knob. A higher parameter results in violent extreme spikes in the rough path. In terms of market implications, a higher volatility deepens the overall convexity of the implied volatility smile. Now, for the memory engine, this is the core functional driver here. Because the kernel weight is t minus u to the power of alpha, with its negative alpha as we said, this integral assigns massive asymptotically infinite weight to the most recent shocks and decaying weight to the distant past. So this represents the non-Markovian reality of the model. Unlike standard diffusion, the current state depends on the entire path history from 0 to t. So now if we simply exponentiate the Gaussian process, like for example this one here, the math expectation would be greater than 1, which is a fundamental violation of the martingale pricing principles. So the solution is to subtract the variance of the Volterra integral inside the exponent, because the exact variance of this Volterra process is n squared, is the volatility of the volatility squared divided by 2 multiplied by this. Subtracting this term stabilizes the equation. So it guarantees that the expectation of Vt given the initial filtration perfectly equals the baseline curve. So when we add these components together, the logic flows perfectly by setting the h to less than 0.5, guaranteeing alpha negative. This produces the rough path, which translates to extreme short-term variance uncertainty. So the market naturally charges a massive premium for this uncertainty on the short-term out-of-the-money options. The result is the exact power law of the at-the-money skew observed empirically. The rough Bergomi framework mathematically enforces that the skew scales with this term. So yeah, now if we look at the theory, now that we looked at the theory, let's look at the computation. Simulating this model presents a massive bottleneck because the Volterra kernel singularity. Look at the graph of the kernel t minus s. As s approaches the t, the negative exponent causes the function to blow up to infinity. This is a mathematical roadblock because of the standard Monte Carlo Euler schemes fails to completely here. So, because basically you cannot simply discretize infinity. So to actually simulate this VT, we must abandon the standard method and deploy what is called the hybrid scheme. So this hybrid scheme is bypasses the roadblock by splitting the Volterra integral. Instead of one flawed numerical approximation, it uses precise exact simulation precisely where the equation blows up, and fast numerical approximation everywhere else. So the architecture requires 4 steps: time discretization, kernel approximation, and singularity handling, and finally the spot variance assembly. Here we divide the time horizon t into n equal steps, and then in step 2 we look at the past time steps that are comfortably far away from the current time t. The power law kernel is smooth and well behaved, so we can approximate this history using the Riemann sum. However, to avoid this ON squared computational complexity, we evaluate this discrete convolution using usually the FFT model, which is a brilliant optimization that reduces the computational cost to n log of n. Now, for the step 3, this is the danger zone, the final tiny time interval right before t, where the kernel shoots to infinity. Instead of trying to discretize this, we use the exact math solution because this is a Gaussian integral of power function. Its variance over this tiny interval is precisely known as this term. Therefore, we don't discretize, we simply draw a random variable directly from this exact normal distribution. Finally, for the 4th step, we combine this the highly efficient FFT with our exact singularity draw to produce the simulated Volterra process. We feed this back into the exponent of the original black box equation, generating a fully realized rough spot variance path. Finally, we pass this into the standard asset price scheme to simulate the log price of the underlying asset. So yeah, that's it. Hopefully you got a clearer image regarding this rough Bergomi equation.